Please try harder. No, not exactly. Thanks everyone for joining me. I'm Scott. I'm a PhD student in Fred's group. And lately I've been working on a compiler for sparse tensor algebra and relational algebra, and working on formalizing its behavior. So going back to Gilbert's opening question at the start of the workshop, does it even make sense to be talking about all these different ideas in the same room? My position is like, yes, totally. There's a lot of recent work that's shown that unifying two or more domains can lead you to systems that generate more performant code, but are also much more conceptually simple. In this talk, I'm going to give sort of a grab bag survey of some ideas related to how mechanical formal verification could actually help us be more productive in addition to creating systems that are more robust. Just to sort of vaguely set the stage, we're interested in sort of high performance computing applications that really need performance, like above all else. And we're talking about relations, tensors, and all that. And we're going to be focused a little more on high programmer productivity. So I'm going to give you a pitch and then try to sort of support the pitch with some work that's been done. So the pitch is, let's continue trying to build domain-specific compilation methods and hardware for relations, tensors, distributions, and factorized things and all that, logic programs as well, within a monolithic repository using the proof assistant Lean. So the immediate qualm may be, why bother with formal verification? I just want to keep on going, making my algorithms faster, like helping people do things, like why should I slow down and try to prove to the machine that what I've done is correct. So I want to ease up on that question a bit and shift your focus away to why don't you think about it as letting the machine help you check some properties of your code statically so that you don't have to think so hard. So a few ways that machine checks can help with productivity are, so in theory at least, if not in practice to a great extent just yet, it could help accelerate implementation. So if you've ever used a static type system, you've probably experienced cases where it helps you find bugs before you run your code. And when we're talking about high performance systems, running your code might actually be itself an expensive process. It might even require re-implementing your code if you're targeting some sort of specialized hardware system. So the more sort of formal reasoning that can happen up front, the better. So the next idea, sort of orthogonal, is that libraries of formalized theories can actually enable different sort of collaboration that happens between large groups of people who sort of combine their efforts into one goal. So I'll talk a little bit about one instance of that. And then additionally, you can potentially help programmers who traditionally are sort of hamstrung, bound to hand implementing their code and going through exhaustive auditing processes, if you can provide some sort of machine checked guarantee. If you've never heard of a proof assistant before, it's just a pure functional language plus an IDE, with the idea being that it helps you build programs and also machine checkable proofs that they do what they're supposed to, where you're totally responsible for saying what they are supposed to do. And Lean is a recently implemented system that's very similar to Coq if you've worked with that, and it's based on dependent type theory, which is just sort of an enrichment of traditional type theory that you would see in a static functional language with types that can depend on values. And this makes it so that you can state sort of arbitrary mathematical statements and talk about them and show that a piece of code, behaves accordingly. So you can think of this as kind of like a database, like a formal ontology for actual math. So I mentioned this word monolithic repository. So I think it's worth considering means of deepening collaboration in this field, because a lot of us are studying optimizations and analyses that kind of apply to central mathematical objects, and we'd be better off if we could share those things with each other. And another side effect of trying to develop a monolithic repository is that decisions kind of happen in public, in the open, it's sort of like a continuous onboarding teaching process when you're working with a monolithic repository, because newcomers, kind of see how things are done incrementally. So there's this question, like, does it even, if you've worked on a compiler, typically they're complex code bases, and so there's this very legitimate question, like, is this even possible to sort of develop a compiler that's open in an academic context? And I'll just kind of briefly point at some work with Coq to do so. So there's this idea of sort of replacing language design with library design. And the idea here is that Chipala and other folks from his group have discussed this notion of sort of libraries of specifications and lowering steps. So the idea is like, rather than building a compiler and then trying to prove something about how it's correct, instead kind of formalize small pieces of that compiler incrementally and then stitch them together in a way in such a way that compilation becomes sort of like a search process, actually. So from amongst the set of lemmas that the different facts about how to turn math into executable code, what applies in this particular situation. And so why dragsters? I think this field is particularly appropriate for this sort of approach, because there is sort of a small core set of mathematical ideas that we could try to formalize. And formalizing stuff is still a lot of work. So this would be kind of a case where we could get a lot of bang for your buck, like a lot from a relatively small amount of formalization effort. We could target many different domains that all rely on tensors in some form. And furthermore, since tensors and relational programming and all that has a kind of a clean mathematical model behind it, it would be nice if we had an existing library of formalized mathematics to help us do our job. And it turns out that there is one. It's called MathLib, and it's been a collaborative open source development for the past several years. And at this point, it's at about 700,000 lines of definitions and proofs. And you might think like, well, I don't know, maybe it takes 1,000 lines just to prove that 2 + 2 = 4. It doesn't. Thankfully, many things can be proved straight from computation, like this fact. And additionally, in a dependently typed language like this, basically everything proceeds from induction, and you really can prove universal statements. So, if you want to prove that x + y = y + x when x and y are natural numbers, you can do so with a few cryptic lines of code. And it's been shown empirically that you can teach a proof-assistant math at about the rate of an undergraduate. So over the past 4 to 6 years, they've gotten through a sort of standard pure math undergrad curriculum, all formalized in one repository, and they're continuing with lots of more quite advanced mathematics. And on top of that, there's a growing interest in scientific formalization as well. So there's a recently funded NSF project, and I think they're calling it SciLib, yes, like MathLib. And this group is focused on chemistry, computational chemistry, and molecular dynamics, with an eye towards expanding towards broader scope. And they have a need to generate efficient numerical computations, as many of us in the room work on. So I'm going to talk a little bit now about how people in the formal verification community have approached very high performance computation. Yes, so the first idea is that First of all, Lean and these other systems are very extensible. They provide extensible notation, and you can think about dependent type theory itself as being sort of like a programmable type system. So another way of understanding what it means to formalize a theory is that you're sort of like formalizing a set of rules that you're going to abide by that tell you, what you can derive. So you can think about a system like Lean as being much more extensible than, say, Haskell in this sense. And one of the primary tools that people use when building proofs are called tactics. And a tactic is sort of the hook you have for programming this like type system thing. A tactic is essentially a program that can look at a goal that you're trying to achieve, the hypotheses that you know, and then it constructs a proof term for you, or it at least makes some progress towards constructing a proof term or a program. So the claim that I'm making here is that this sort of goal-driven development might help improve programmer productivity. So there's one example, this paper by Liu et al., scheduling a dense tensor language, and their contribution here was exhibiting this like clean, pure functional intermediate representation for tensor computations, and then formalizing some rewrites rewrites on that intermediate representation. So they were able to take what were previously considered sort of low-level program transformations and translate them into this higher-level representation, which was much easier to reason about, which sort of enabled this work to happen, I think. And another thing that this work kind of advocates for is, I think, is treating the theorem prover as sort of a workbench for the programmer. So whereas a compiler, might decompose logical specification of a program from kind of low-level optimization concerns for it, when you do this in a proof assistant, you can kind of go one step farther because you can state all the preconditions that these low-level optimizations need. And if you try to apply them in an invalid way, your proof script simply won't proceed. And then you can, then ask the mailing list, like what's going on. But you don't end up with incorrect code. And then in a sort of similar vein, there's a project called Silene that is seeking to help people express their algorithms in a very direct mathematical way, leaning on the library of math that exists in Lean. So here, the idea is that you start from sort of a high-level specification. You apply whatever sort of transformations you want to that mathematical expression without any low-level concerns yet. And then you use the tactic framework to incrementally replace the parts that are difficult or impossible to compute with things that actually can be computed. So an example from this project is you can write down a Hamiltonian for, this is, I think, a simple harmonic oscillator, in more or less exactly the form you would see in a textbook. You can then state that you want an implementation for this system, and then you can derive that implementation incrementally using a tactic script. So this tactic script first unfolds the definitions. That's the first line. I apologize for this not being interactive, but after unfolding the definitions, we see that we need a couple of derivatives to solve the system. So we apply this autograd tactic, which replaces the sort of exact mathematical derivative with a particular implementation. And then we choose a solver method and say that we want to approximate the solution using that. And then finish the implementation. And then this produces code that you can just build and run. And you get a little funny harmonic oscillator thing. And then just to kind of start wrapping things up and bringing things back to dragsters again, there's been quite a lot of recent work on intermediate representations for sparse tensor algebra and all the sorts of things that can be expressed that way. So Amir has created the semiring dictionary query language and quite a lot of subsequent work. And I'll be presenting some work at PLDI here on Monday that likewise sort of fuses relational and tensor algebra and sort of transforms the mathematical the mathematical meaning into a more computationally reasonable representation, but then combines these representations in a sort of natural way that's amenable to formal reasoning. The sort of benefit you get from these systems is that you can produce a much smaller code base that matches the performance of previous systems that were more like kind of narrow. And then finally, I would like to go into more detail here, but I guess we're short on time. Another sort of avenue for proof assistants to have an impact on these high-performance systems is sort of organizing the details of the backends that you need. So, you know, a variety of work considers different pointer-based data structures for traditional CPUs and how to deal with all the complexity of generating code for these things in the service of tensor expressions. But there's an ongoing amount of work creating altogether different, you know, processor architectures going beyond sort of the pointer machine. You know, a proof assistant, again, can kind of help organize the preconditions and details of validity of the different implementing components. And I just want to highlight that another colleague from my group is presenting on this subject here at PLDI on Monday. Yeah, that's what I've got.
So why don't we take one question while the answer is getting set up? Do you have
any? So let's say I have a proof in Lean about, let's say, real valued functions that are continuous, and that I can compute the derivative. And then can I then use as a tactic script to compute the sort of the derivative of my program?
Of your program. Yes, maybe in sort of a trivial sense. If you've specified a program using a certain function, then you know perhaps it's valid to simply replace that program with the function and then the derivative. You don't automatically get a way of sort of efficiently calculating the derivative or like producing an equivalent program that calculates the derivative, though. You know, it's possible, for instance, to have a very complex program with a simple specification that you can differentiate, but without you know, necessarily having an efficient like implementation of that derivative, I guess. So there's kind of another piece needed to sort of tie that together, I would say.
Okay, so I can't really sort of extract the program, or maybe I can. I don't know if I get it.
Yeah, it's a little unclear. I think it depends on some other details.
Okay.
Yeah, thanks. Let's thank Scott again real quick.